Bismillahirrahmanirrahim. Assalamualaikum and hi everyone. In this video, we are going to present our project entitled One-Step Rapid Synthesis of 94.78% pure gold nanoparticles without post-processing. Before we begin our presentation, I'd like to introduce to you guys our project members. My name is Kara Dibinisa. We have Miss Nur Atika Azman, Puan Anis Diana Rosli, and Puan Aida Zulia Zulhani. Our project was supervised by two respected lecturers, Dr. Nur Shahnia Muhammad Hadis and Dr. Nur Azwana Muhammad Najib.
I will begin the presentation by highlighting the novelty and strength of our method. This work used an optimized citrate to gold ratio of 2.3, which lies within the reported range but is fine-tuned for better performance. Combined with a reaction temperature of 90 degrees Celsius, the method yields high purity gold nanoparticles directly with no need for additional purification steps like centrifugation or dialysis. In summary, the method offers clear advantages in terms of time, cost, and also scalability. It enables fast synthesis in just 11 minutes, eliminates time-consuming post-processing, and simplifies the overall workflow. Next, I will provide some background on gold nanoparticles and explain the problem this work is aiming to solve. Gold nanoparticles, or AuMPS, are highly valued in nanotechnology because of their unique optical, electronic, and catalytic properties. These features make them ideal for application in biomedicine, sensing, and also catalysis. One of the most common methods for synthesizing AuMPS is the Turkovic method, known for being simple, cost-effective, and water-based. However, a major challenge with this method is that it often leaves excess citrate and other impurities, such as chloride ions, in the final product. This becomes a serious issue in biological application, where contaminants can interfere with accuracy and cause misleading results. To address this, our study focused on optimizing the citrate to gold ratio and reaction temperature to create a method that is efficient, reproducible, and produce high purity NuMPS without the need for post-synthesis purification.
This prototype demonstrates the synthesis of two nanoparticles using a fast and cost-effective modified Turkovic method, suitable for large-scale production. Step 1. Preparation of solution. Two solutions were freshly prepared in deionized water, 0.8 millimolar gold trichloride, 34 millimolar to sodium citrate. Both chemicals were sourced from Sigma Aldrich and Fisher Scientific. Fresh preparation ensure consistency. Step 2. Synthesis of gold nanoparticle. The gold trichloride solution was heated to 90 degrees Celsius with stirring at 1000 rpm. Once boiling, trisodium citrate was added to achieve a citrate to gold ratio of 2.3. Within 11 minutes, the solution turned blackcurrant, indicating nanoparticle formation. Heating stopped after the color remained unchanged for 5 minutes. The solution was then cooled to room temperature and stored at 4 degrees Celsius for analysis. No purification steps were needed. Step 3. Sample preparation for EDX. To analyze elemental composition, 50 microliter of the gold nanoparticle solution was dropped on a clean glass slide. It dried at room temperature for 48 hours, then baked at 100 degrees Celsius for 50 minutes for better adhesions. Finally, EDX analysis was done to confirm the presence and purity of gold. This method provides an efficient, reproducible, and scalable way to synthesize high-purity gold nanoparticle.
Thank you, Puan Aida Zulia, for walking us through the synthesis process. Now I will show you how the final product, the gold nanoparticle, actually looks like. Figure 1 shows the gold nanoparticle synthesized using the Turkovic method with a molar ratio of 2.3 carried out at 90 degrees Celsius. As you can see, the product appears as a colloidal solution with a deep black currant-like color. This distinct color suggests the formation of gold nanoparticle, and it can be influenced by factors like particle size, shape, and concentration. Figure 2 displays the morphology of this nanoparticle under an ultra-high resolution scanning electron microscope or UHRSAM. This allows us to closely examine the size and shape at the nanoscale. Although several characterization techniques were performed, such as zeta sizer and UHRSAM, in this presentation, I will focus specifically on the EDX results, which I will explain in the next slide. Here is the elemental composition of the synthesized AuMPS as analyzed using EDX. This table presents the elemental composition of the synthesized AuMPS based on EDX analysis. As shown, the dominant element is gold with a weight percentage of 94.78%, which strongly suggests that the synthesis was successful. Minor elements such as carbon, oxygens, and trace sodium were also detected, likely from residual reagent during synthesis. Notably, chloride was not detected, which aligned with our expectation post-synthesis and purification. While these results are promising and support the successful of AuMPS formation, it is important to acknowledge that EDX is not surface sensitive and doesn't provide information on chemical bonding or oxidation states. To gain a more complete and accurate understanding of the surface composition and purity, X-ray photoelectron spectroscopy (XPS) is planned as a follow-up. This will allow us to confirm the chemical states of gold and ensure there are no unwanted surface contaminants. So, while this EDX data give us a strong starting point, we are taking it further to ensure the quality and reliability of our product.
Assalamualaikum. Now moving on to the contribution and the impact of this innovation. We have developed a one-step method to produce 94.78% pure gold nanoparticles using a modified Turkovic method with a citrate to gold ratio of 2.3 at 90 degrees Celsius, and it requires no purification. The synthesis is completed within just 11 minutes with a clear color change that allows easy visual monitoring, no need for expensive equipment. So this method solves the speed versus purity trade-off, offering a simple, cost-effective approach suitable for labs with limited resources. It also removes the need for post-processing, making it easier to scale up for industrial use. Overall, it enables faster application of gold nanoparticles in biomedicine, catalysis, and electronics.
Now let's move on to the market potential. Gold nanoparticles are essential in biomedicine, diagnostics, sensors, and electronics. Commercial gold nanoparticles can cost up to 4,610 ringgit for just 5 milliliter due to the strict specifications. Our method is significantly more cost-effective by eliminating purification steps and allowing size control through synthesis parameters. This makes it ideal for custom applications, especially in low-resource labs or scalable industries, giving our method a strong market edge in both academic and commercial settings. We have successfully synthesized 94.78% pure gold nanoparticles using a modified Turkovic method at lab scale without purification. The product has been characterized using EDX, UV-Vis, Zeta Sizer, and UHR SAM, all showing promising results. Our next steps involve electrochemical studies using CV and DPV to test heavy metal detection. This innovation is now ready for pilot scale development and has clear potential in environmental sensing applications. Thank you everyone. I hope you enjoyed the presentation. Bye bye.